Hi everyone, it's Rebecca Flicher. I was assigned section 3.1 number 7 for this video presentation number 4. So for this problem, there are 3 steps we have to do. The first is to find a power series solution of the differential equation. Then we want to identify the series solution in a familiar elementary function that we know from before or in a book that we've read. And then you want to determine the radius of convergence. So our problem is that we are given 2x minus 1 times y prime plus 2y equals 0. So the first thing we want to do is find our y and y prime that we want to use for substitution. So our y we want to be the summation as n equals 0 to infinity of cn x to the n. And then once you take the derivative of that, you actually get, for y prime, the summation of n equals 1 to infinity of n times cn x to the n minus 1. Now the reason why n equals 1 down here is because you can't have a negative exponent up there for what we're doing, because if you had a 0, it would be 0 minus 1, which would be minus 1, which doesn't work. But you can have to the 0, so 1 minus 1 equals 0, so that's why that works. So the next thing we want to do is actually substitute our y and our y prime in. So when we substitute, we get 2x minus 1 times the summation as n equals 1 to infinity of n times cn times x to the n minus 1 plus 2 times the summation n equals 0 to infinity of cn times x to the n. So from here we can distribute out our 2x and our negative 1. So we end up getting a summation of as n equals 0 to infinity of 2n cn x to the n, because the x here will change the x to the n minus 1 times the x gets x to the n, and then minus the summation n equals 1 to infinity of cn x to the n minus 1 plus the summation of n equals 0 to infinity of 2 times cn x to the n, because this 2 here can distribute out to our y that we had right here. So right now what we're going to have to do is we're going to have to shift the index, because our n equals 0, so they're not all the same. So you want them all to have the same value there. So we're going to shift the index, and when we do that, we're going to let k equal n minus 1, which means that n equals k plus 1. So when we plug that in, we get the summation n equals 0 to infinity of 2n times cn times x to the n minus the summation k equals 0 to infinity of k plus 1 times ck plus 1 to x to the k, because we're substituting in our k plus 1 for our n. And then you're going to have that added to the summation of n equals 0 to infinity of 2 cn x to the n. So now that we have substituted our k in for our n, we can actually now resubstitute in our n again, because we know what our n is going to be with that. So you're going to resubstitute your n in, and then you end up getting the summation of n equals 0 to infinity of 2n cn x to the n minus the summation n equals 0 to infinity of n plus 1 times cn plus 1 times x to the n plus the summation n equals 0 to infinity of 2 times cn x to the n. So with that, they all have the same summation, so you can actually pull that out in front here, and they're all times x to the n, so you can pull that out as well. And then what you're left with in the inside there is 2n cn minus n plus 1 times cn plus 1 plus 2cn in that inside area. And then you can simplify that even more. So you get 2n cn minus n plus 1 times cn plus 1 plus 2cn. And then from that, you actually can end up getting, because the 2cn here and the 2cn there, or 2ncn, you can have those be added, and then you end up getting 2cn times n plus 1 from that equals n plus 1 times cn plus 1. And then from there, if you divide this n plus 1 out from there, you get 2cn equals cn plus 1. I know that's a lot to take in with all those n's and c's and all that stuff, but hopefully it was easy to follow with the work there. So from there, we are now going to do our next step, which is actually solving for our C1s and stuff, our C1, C2, C3, C4, and so on. So we want to find that general equation. So the way we do that is to kind of solve for the first couple. So we know that Cn plus 1 equals 2 of Cn, 2 times Cn. So when n equals 0, C1, which is our Cn plus 1, so 0 plus 1. So our C1 equals 2 times C0, C naught. And then you can do this for several n's. We're going to go up to 3 n's. So then you have n equals 1. So here your C2 equals 2 C1. Well, we know up here that C1 equals 2C0 or C naught. So you can actually do 2 times 2C naught equals 4C0. And then you do it again for the n of n equals 2. So you get C3 equals 2C2. So we know from above what C2 is. So you get 2 times 4C0, which equals 8C0. And then n equals 3, you get C4 equals 2C3, which then equals 2 times 8 of C naught times 2 times 8 C naught, which equals 16 C naught. So from there, we actually can see a pattern. So you have, for your n equals 0, you have 2 C naught. For your n equals 1, you have 2 squared times C naught. Then for your n equals 2, you have 2 to the third C naught. And then when n equals 3, you have 2 to the 4 C naught, and so on and so forth. And as you can see, it keeps going up. So going up by the n. So what you have here is Cn equals 2 to the n. That's kind of our general equation there. So what we do is we are going to try to solve for our y of x in terms of that. So we have y of x equals the summation n equals 0 to infinity of Cn x to the n. So what you want to do here, we're going to say that it's equal to C naught, so plus C1x plus C2x squared plus C3x cubed plus C4x to the fourth, plus and so on and so forth. And then from there you can actually plug in what we found up above. So you get C naught plus 2C naught x plus 4C naught x squared plus 8C naught x cubed plus 16C naught x to the fourth, and so on and so forth. So then once we actually plug in those numbers that we have, you have here our solution for the first part of our problems. Y of x equals C naught, which you can pull out, and then you get of 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the fourth, and so on and so forth. So that's kind of what our first answer to our solution is. That's our main one. So now the next step was to find it in a way that is in like terms that we've learned before, like those kind of things. So if we remember equation 11, it says that 1 over 1 minus x equals the sum of n equals 0 to infinity of x of n, which equals 1 plus x squared plus 3x squared, and so on. So knowing that, we kind of look at what we have, and as you can see, that exactly is what our thing looks like, except the only thing is that we have a 2x, not just x. So that means while this general equation is 1 over 1 minus x, what ours is going to be is 1 over 1 minus 2x, because that's what our quote x value is for this problem. So we know that it's going to be times our C naught value. So our problem answer in terms of functions that we know from before would actually be y of x equals C naught times 1 over 1 minus 2x. So that would kind of be that answer for that. And then lastly, we have to find the radius of convergence. So as we learned before, rho equals the limit as n approaches infinity of the absolute value of Cn over Cn plus 1. And so we can plug in what we know our Cn value is and our Cn plus 1 value would be. So as we know, it's 2 to the n is what Cn equals. So rho equals the limit as n approaches infinity of 2n over 2n plus 1. So put it over here, and we actually end up with something we've learned before. You have the limit as n approaches infinity, supposed to be right there, of 1 over 2n plus 1 minus n, which just gets us 2 to the 1, which just equals 2. So you have limit as n approaches infinity of the absolute value of 1 over 2, which gets us 1/2. So our answers for this problem is, for the first one, the general solution is C0 times 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the fourth plus ... And then the one in terms that we know is going to be, of terms that we've seen before, is going to be y of x equals C0 times 1 over 1 minus 2x. And then lastly, we found our radius of convergence, which is our rho, which equals 1/2. I hope this helps you out, and that's just how you do the problem.